Cool. Thank you, Marianka. As she has said, I'm Michael. I don't have much more of an intro than that. I'm a security researcher at Orange Cyber Defense, and I like to break stuff. And I like to buy things that are already broken so I can fix them, because then they're cheaper. Yeah, so that's my name. I have a background in DevOps stuff. Studied electronic engineering and pivoted sort of into the software stuff. I'm a Hex Coffee Joburg / HexCon / former B-Sides organizer, so you may have seen me if you're involved in community events, and if you're not involved, you should get involved. Obviously, thanks for coming to HexCon. That's really great of you. Yeah, social media handles and kind of a rebel. By that, I mean we had this random thing where at work we were told there was going to be a photographer taking pictures of everyone, and they said, if you want a headshot, come and do it. So I figured, well, I might do a talk one day, so let's go. And then I asked the photographer, because he was telling me how to stand and how to smile and how to look, and I said, can I cross my arms in front of me? And he said, no. So. And that is the only picture I will use of the ones he took. So. Right, so getting straight into it, the topic of my research was this thing. You've probably seen them around. Basically, you put your hand near them and something happens. Typically, they let you out of places, hence the exit printed on the bottom. That's how they come. I didn't put that there. And that's as much as there is to it. So I saw them and I kind of wondered, how do they work? I've seen a bunch. These are some pictures of ones I'd seen that I've spotted in the wild in South Africa. They all work in the same way. The sensitivity varies. Sometimes you actually have to touch them and disobey, but most of the time, from 5 to 10 centimeters away, they work. So, yeah, they are all over the place. Access control, which is kind of where we're going to be focusing. So often, yeah, so that's where they were used. So that ticket issuing, so I think in Joburg, it seems to be a uniquely Joburg thing, but there are booms and spikes that will puncture your tires, and they go down when you do the thing, and I assume that if something happens, there's kind of a lockdown, and you can't, doing that doesn't do anything, and you can't run away. That's my assumption. And then boom opening for parking areas. Yeah, so ticket issuing and boom opening. The thing that piqued my interest in why I started asking the questions about how this thing works is because I noticed that at a place, a tech company, they had these things inside access controlled areas. So on the outside, you use a key fob or a fingerprint or a PIN code or whatever, and lets you in because it's a unsecured area. And then the secured area had one of these things to let you out because you're already in. So kind of like logging in and logging out. Logging in, you need authentication. Logging out, well, you're leaving. It's fine. So anyone can do it. But I noticed that the thing dividing secured from unsecured was glass, and that is. I don't actually have any speaker notes. They disappeared. Anyway, so I had a couple of theories on how do these things work. There were a couple, from my electronics background, I had some theories, these are the only possible ways I can think of that they would function, limitations aside. So ultrasonic, we're using audio, so that would require some kind of a way for sound to get out, and there isn't that. Radar, which would work, would be really expensive, and I don't think it's a good application for this. And then the last one's super common, you see in all kinds of stuff, is optical. So essentially you bounce a light off something, and depending on how much of that light is reflected, you can tell if there's something there. So it's used for robots, for detecting objects and making sure you don't smash into things. Another hint was the color of the lens, which is why I took that picture with the flash on. So it's not immediately obvious if you look at one of these, but with direct sunlight or a flash, you can see there's sort of this red tinge. And that's quite common because red plastic will permit red light, and infrared kind of falls into that area of the spectrum. So it's the same as how old 3D glasses used to work. Blue lens permits blue light, red lens permits red light, and so you can see each side with either eye. So this is our first hint. We're probably dealing with IR reflectance because of the reasons mentioned above. The other thing with IR reflectance is that it's really cheap to implement, so that kind of adds to my suspicions. And obviously the next thing is I bought one. Cost me 270 Rand on Take-A-Lot. And that allowed me to obviously take it apart, which is why I like buying broken things. I want to see how they work, and I want to fix them. But in this case, I really just wanted to know, how does it function? So if you have a look inside of these things, you can see the backside, there's not much. There's a little adjustment for how sensitive it is, which answers my sort of back of my mind question of why do some of them work really close and some of them far away. And then on the other side is all the magic that makes it happen. But you can see that there's a very obvious LED in the middle. If you're familiar with what an LED is, that should be clear. And then to the left of that, less obvious, but that is a infrared receiver. So IR reflectance seems to be the thing. Something else that was interesting is I purchased this in November 2019, which also shows you how long this research has been sitting on my shelf. But the production date was June 2019, which shows that they were being produced pretty rapidly. And yeah, usually a short sort of window means that it's a mass-produced item and it's quite actively in production. They didn't make 1,000 of them, and now they're trying to clear out stock. You also notice that 2019 was 1 year before 2020, where people got really into not touching stuff. So sales kind of escalated beyond that. And then in the plastic housing, at the back of it, there's a shroud. So essentially all that does is stop the emitter and the receiver from picking each other up directly. It has to bounce off something. So that's what that did. So time to figure out how it works. So we break out the main tool that you want as a hardware, like enthusiast or even vaguely interested, a multimeter. This is a somewhat fancy one, but the mode I use for this is the one where you touch the leads and then it makes a beep. So if the two leads are connected, it makes a beeping sound. And so that is incredibly useful for sort of tracing out what things are connected to when it's not immediately obvious. So from that, I got this breakdown of what's on here. What it is not entirely important at the moment, but you can see there's the relay, which will open the door, trigger the mag lock or whatever. The LED is showing the blue or the green light that it's open or not. The LED is the little controller that does all the logic behind it. And the transistor, which I will come to just now, that is important. So initially, I just did a sort of nominal test, adjust the sensor to work from 10 centimeters away. So if I can get it to work from further than that, then I could easily calculate, it's 10 times, 20 times, 100 times the distance. So just to backtrack quickly, the purpose of this research was to see, can I open these things through a glass door without being in the authenticated area? Obviously, that means I will need some range. So attack number 1, super simple. I've already figured out now this device emits infrared and detects some reflection. Your hands are reflective, but not that much. Interesting thing is that skin color doesn't matter much in the infrared spectrum. The color of skin is more a visible light phenomenon. So that's useful. So mirrors are obviously more reflective than hands, so let's do mirrors. So I try to take a picture of a mirror for you. I promise it's a mirror, you just have to believe me. So it was a big, flat, normal mirror, and I kind of tried to line it up as best I could and trigger the sensor with the mirror. The best I could get was 60 centimeters, which, if you look at it relative to what it works at, is 6 times the nominal range, which is cool, but not super helpful. And the reason is this is kind of what an attack would look like. I drew this myself. So you have a glass door or a glass wall. We are assuming that the barrier is glass because we want light to pass through it. That's one great thing about glass, is light can pass through glass. And then we want to bounce it off the wall in most cases. So the little sort of V pattern in front of the no-touch sensor is showing the receive sort of angle is really limited. So if you can get like around the side of it, that doesn't really work. You have to be sort of coming head on with whatever you're sending it, the reflection or whatever. Now, the amount of light that's emitted from this thing is so weak that even with the standard mirror, I could only get 60 centimeters. There is no way that's going to bounce off a wall. So anyway, let's try another mirror. So funhouse mirrors, they make your hands look really big. the idea is that, as you can see on the left there, a concave mirror. I used my wife's vanity mirror. I gave it back eventually when she came looking for it. The idea is that the sort of light beams converge at a point, and so at a set distance, you've got like a crazy amount of magnification, basically. So whatever light waves are hitting the thing get magnified and reflected to that point. There's a bit of a flaw in this theory because that point is a set distance, and you can see the waves they go in the other direction. Can't do that with my hand, but basically the image just ends up becoming inverted and upside down the further away you get. But it's a start because it does increase, it increases the amount of light reflected and it focuses it in one point. So I tried this out, got 2 meters of range, which is crazy. It only works at 10 centimeters if you put your hand there, but 2 meters is it's getting into towards usable. And yeah, you can look at a best case scenario if they're configured for 20 centimeters and you get 4 meters line of sight, which is great. But as I said, a lot of the time they're set for 5 centimeters or 0 centimeters. The reason they're no touch actually is because if you're if you're physically touching it, there can be no reflection. So 1 centimeter is kind of the closest you can get. But you can touch it, it's fine. I won't tell anyone. The catch here is the line of sight part. So right now I'm taking a emitted light source, I'm bouncing it straight back at the thing with as a reflective surface as I can find. This is another picture I took. It's of a wall. In this case, you cannot see myself or my phone. In fact, you cannot see anything. And that is because walls are not super reflective. Walls scatter light. So this line of sight thing is kind of not really working in our favor. Right, so back to the hardware. So we start looking at it again. This was a very useful piece of information. So this is a sensitivity knob, right? So you can make it can basically just stay on permanently because it bleeds through the shroud, or not work at all. You can turn it down to nothing, and then literally it doesn't matter how close you get, it doesn't switch. But the sensitivity is a key thing here. We're not actually adjusting the sensitivity. The sensitivity of the device is constant because this adjusts how bright the emitting light is. So that means if we bring in an external light source, we're dealing with a fairly highly sensitive device, regardless of what this is set to. So we don't want to use the emitted light source because we can get 4 meters at best, not reflected off a wall. It's not really viable for any kind of practical real-world attack. So yeah, the hint number 2, sensitivity is constant. We don't have to worry about the adjustment there if we start bringing our own light source into it. So then we can kind of get into the nuts and bolts of how this thing works. So this is a picture of a logic analyzer. It's got pretty colored cables, and it essentially gives you a trace of signals on some hardware device over time. It doesn't show you, it's not an oscilloscope. It doesn't show you exactly what the voltage is. It's for digital applications. It just says it's high or it's low. So it's 1 or it's 0, that's it. Which for a lot of applications is really good. That's useful enough. And then you get these handy little clips that clip onto a thing so that you can easily connect to them. Because those wires are, they're small and they're fiddly and you don't want to have to solder stuff. It's just a pain. So now that it's there, we can switch it on and we can see what is it doing. So initially, you can see that's over a 5-second span. There's just the signal that's up and down, up and down. If you zoom into it, that's what it looks like. It's up and down, but bigger. The question that I asked here was, why are there solid blocks and not a square wave? And if you zoom in even more, you can see it's not actually, it isn't a square wave. It's a signal, super, that's point whatever of a millisecond. It's a 30 kilohertz signal when it's on, and it's 0 when it's off. So those are the 2 states, the binary high and binary low. Which is interesting. It's not just on light or off light. It's pulsing. So why is that? And the reason is that basically infrared is everywhere. Like I'm emitting some amount of, everyone is emitting some amount of infrared. The sun, the heat that comes from the sun is infrared. It's just kind of naturally occurring, much like visible light is a naturally occurring thing. So here's a picture of a dog. Infrared is commonly used to measure the temperature of something based on its very specific wavelength, but this is, this is how it's represented in a way that we can see, because humans cannot see infrared light. This is a problem when you're experimenting with this stuff, because if you're shining infrared lights all over the place, you can't see if you're blinding yourself. But anyway, so the point is, the dog's mouth and eyes and ears are the hottest part of it in this picture. And if, for argument's sake, it isn't, but if it was in the right sort of wavelength of infrared light, then if this dog opened its eyes in a room, the door would open. And that doesn't work. I don't know why the dog's in a lab, but that doesn't matter. The point is, we can't just rely on amounts of infrared light being high or low. So how do we solve this problem as implementers, not as attackers? So back to this little guy. You will see it very specifically says, this isn't the data sheet for this, I will disclaim that, but they are functionally all pretty much the same. They all work similarly. They're a common enough component. It's the same thing that you have in your TV or anything that uses an infrared remote to receive that infrared signal and then do something with it. So the 30 kilohertz thing, it's a spec on the thing that will only react at 30 kilohertz. So if you have a look at the waveform, on the top is what the LED is doing, the emitter LED, and on the bottom is the signal coming back from the receiver. So as you can see, it's not that 30 kilohertz waveform, it's a solid pulse. So what's happening is it's decoding the 30 kilohertz waveform and it's saying, okay, I'm picking up a valid signal, let's do that. Because 30 kilohertz doesn't really, infrared doesn't really occur naturally, that's not a thing. It does, but we'll get to that later. But it does a pretty good job of filtering out, saying this is what I expect, this is probably from, a valid transmitter, and I'm going to pulse and then send the signal off. So that's cool and all, but I noticed something immediately is that those don't line up. So the device I'm measuring this with measures all 8 channels it can do at the same time. So these are completely aligned. So the actual timing differences there are real life timing differences. And so it starts raising the question, why is there a delay? So I measured this, see it's 284 microseconds. And so that's not a lot of time. Maybe it's the speed of light. Maybe it's like the physical distance, because there is, distance to travel and it's times 2 because it's a reflection. So let's see if that's a thing. So I calculated it, and that's 85 meters, which is not, it's not 10 centimeters. So clearly it's not the speed of light. It's not just the time it takes to bounce off my hand. So we get back into the data sheet. Data sheets are fantastic if you know what hardware you're dealing with. This device in particular, the 8-pin chip that does all the logic, actually has no inscriptions on it whatsoever, which is quite common on cheap mass-produced hardware. But anyway, I know what this device was, so I could look at the data sheet. Right, so now we're going to get a deep dive into electronics. I'm kidding, it's just stuff. There's a lot of stuff. Look at how many boxes. There are multiple boxes inside here. And what it does doesn't matter. But the point is, there's gain and bandpass and demodulator and whatever. And there's processing happening. It's not just an LED. So it's actually doing stuff. And it's trying to filter out noise and trying to make sure that what signal you get in is what you're expecting. So it's busy, and this is probably processing delay in this case, because 85 meters, it's just not that. The other thing I noticed from the data sheet is, again, the details don't really matter here. The point is, essentially what that's saying is that the pulse will go low after between 10 and 15 pulses from the emitter. So the top would be the emitted signal, and at the bottom is the output. And what I'm interested in here is that the delay between, for it to turn on is not constant, which is handy, because we'll get to that in a sec, but that's something to note. But that answers our question. That's why there's a delay. It's waiting for between 7 and 12 cycles, ideally 10, it says. In this case, it's 9, before it does something, so that you get a valid signal. So this introduces another hint, which is that these devices might have some tolerance. Now this brings me to an important point of hardware hacking or reverse engineering. In software, there are sort of finite variables, and often you can make a lot of them go away with using Docker. But in the real world, like, there are so many things that come into effect here, and it's, if it's too hot or too cold, the traces are too thin, external interference, like lights in the room, these are legitimately a problem for optical applications, because these don't only emit visible light. They almost always bleed into a little bit of either side of the spectrum. So timing variances, power instability, all of these things, they apply. And the reason this is important is because you have to design for this stuff. You can't just, make it exactly to spec and hope it works, because the real world isn't that forgiving. What this means is that we can take advantage of these tolerances. And it means that we don't have to be exact. We can start taking advantage, and we can, sort of fuzz our way through this. And that often gets you further than you'd think. Right, so I'm looking at, again, this is just traces of me actually using the device, putting my hand in front of it, seeing what happens. That red line going high is the relay getting a positive pulse, saying the little chip that decides if you're allowed to pass or not. That switches on a relay, and this will open a door or maglock or whatever. What you do with it is up to you, but the point is that relay going high means door open, we're in. So you can see sort of it progresses from the top is what's emitted, and the blue is what's received by the receiver. So as I bring my hand closer, you can see more of that emitted light is demodulated and decoded by the receiver and sent to the chip. And eventually at the end, where it pretty much lines up, I can enter. Once it's opened, it stays open for about a second. It's like 800-900 milliseconds. Then it sends out another pulse to check that you're still there. So if you hold your hand in front of it, it will stay open. And then at the end, you can see there wasn't enough of a positive match for it to stay open, and the relay closes again with the red line going down. So, I made these slides in PowerPoint. I exported them to Google Slides. I changed the theme, and then I downloaded it again, and then put it in PowerPoint, and this is what I get. So the next thing is to emit a fixed signal and see if it responds. So you can see there's a pulse. It's pulsing for a set time and then quiet for a set time. So I figured, well, let me just make a device that pulses like this thing is doing, emits infrared at those frequencies, and then see what happens. So with a logic analyzer, you can do some timing measurements. So you can see the pulse is high for 14 milliseconds, quiet for 30. The details don't matter that much, but that's my input to sort of create an initial attack attempt. So I did it. The top line is the spoof signal. The middle one is what's actually being emitted by the device. And you can see the receiver is picking up my 30 kilohertz signal and triggering like I expect it to. So I thought, well, this is a good start. And obviously, there were timing differences there, which is also important. But I figured because I wasn't being very exact, like I was taking advantage of the tolerances, I figured eventually, like if the timing differences are off slightly, it will drift into phase with what's being emitted, and it will think that it's a reflection. Unfortunately, I was wrong. So this is the point where it starts drifting quite drastically, because I really didn't try very hard to make it the same. But you can see as soon as my signal overlaps with the emitted signal starts to change. And this wasn't great. So we got past the first thing. It's responding to something I'm doing, but it's not opening the relay. I don't have the relay thing there, but nothing happened, so I didn't screenshot that. So yeah, if you zoom in, you can see there's my signal overlapping with the emitted, and it's completely different now. And how am I supposed to detect that it's changed from this tiny little LED that's barely doing anything? So this is the end of my talk. No. In truth, it was not the end of my talk, but or the end of my research. But I did kind of put it away because at this point I was kind of frustrated. I hadn't spent a ton of time on it, but I thought, this is going to be an easy win, and it wasn't. And then I just came up with artificial reasons why this was going to be, my theories were complicated as to why it was doing this and how it was working. So based on that, I was like, oh, this is a huge mountain. I'm never going to get over it. Can't do it. Too bad. But what I did realize is, one, artificial hurdles, like don't get stuck on something that you think is the case. I don't know it for a fact. And trying stuff that doesn't work also gives you insight into how a device behaves. This is true in software as well. So that insight is quite valuable, and so often it's useful to just try stuff. And if it doesn't work, you learn something more and you narrow down what you're going to do. So the next thing, security versus reliability. So this is kind of where I got stuck. I assumed that this changing pattern was a security feature. In reality, a feature implemented for reliability can look a lot the same as an thing implemented for security purposes. So the changing pattern was confirming that reflections were being detected. So somebody's got a remote that works on the same carrier frequency in the room and is blasting a thing, or I'm trying to open or whatever. Or there's another no-touch sensor somewhere in the room. That's another thing. If they're set like way too sensitive and they're blasting each other, like that would be chaos. So the changing pattern was obviously confirmed, but was it security related or not? So I was looking at it and thinking, there's nothing else here. There's just a changing pattern. There's one variable that's different here. There's no fixed offset. There's no changing pattern. None of that stuff is happening. And also, if I look at the timing of it, like it's not super accurate. They haven't spent a lot of money to make this like cycle precise. So in this case, it turned out to be an anti-interference feature. It was not a security feature, and as such, it only needs to be resistant to naturally occurring events. It doesn't have to be completely foolproof. And even if that wasn't the case, like going in with this mindset meant that I tried some other stuff and I figured out where to go from there. If I was wrong, well, then it's security and then it's secure, and you give them a 0 findings report and walk away. So taking a step back again, looking at the device itself, what are we dealing with? It's a mass-produced device. There's no branding anywhere, not on the PC board, not on the box. There's a vendor that sells them under their name, but they sell a bunch of stuff that doesn't have any branding on it, so they're just reselling Chinese white-labeled stuff, and that's what this is. It just needs to be reliable. It doesn't necessarily need to be secure because, again, we know this with software. Who's looking at this stuff? Like, if no one's looking at it, then it doesn't matter. But I'm here today, so I guess that's not always true. So it just has to work reliably. And if they were to implement strict security features, it would take money, time, increase the chances of it not working. Like, it's just not actually worth it for the most part. And it would make them more expensive. Probably wouldn't cost 270 Rand if they'd spent thousands of man hours implementing security features. So let's test and figure it out. In steps 3D printing, and this is one of my favorite things. So anyone who's ever seen a 3D printer or used a 3D printer has 100% gone to Thingiverse, downloaded a thing, and printed it. And that's cool for like the first 5 prints once you get it like reliably working. But I find so much satisfaction, and maybe it's just me, but in designing and making a thing that's purpose-built for the application, and then having it in your hands, so this is the actual print. It took probably 2 hours start to finish of printing, and that just blows my mind. Anyway, this was my attack. So I bought this LED in 2019 when I originally got the sensor. So that is a 10-watt infrared LED, and for context, it's the smaller floodlights you can buy for outside. So they'd comfortably light this room up. Not quite as much as this, but you'd be able to find your keys on the floor if I had one 10-watt light in this room. And then the lens serves to sort of focus that beam. So I'm not going to demo it now, but if I take my phone and switch on the torch and put the lens in front, like if I shine the torch around, you can see my torch is on, but that's about it. If I put the lens in front of it, it focuses the beam to a point where it's probably not more than a meter on that wall over there. It's just hard to see because this room is very well lit. But the point of it is obviously take that 10 watts and direct it all in the direction I want it and see what happens. So, attack number 2. There was a possibility this could be a closed loop. Well, it was a closed loop system because the system controls the input and the output. and the tolerances only have to account for the amount of time for the light to get from your hand and back. Luckily, we have other tolerances that are working in our favor. So yeah, the next thing is if the changing patterns for security, it becomes hard. So if it's like being very stringent on timing, then we're going to struggle to get it to lock up exactly, and yeah, it's just going to be tough. I do have a bit of a leg up here because I was able to physically measure the pulses and get exact timing. But yeah, it would be difficult to replicate it exactly. Then the next thing is if it's only for reliability, then maybe the tolerances will let us have a go. So I figured instead of emitting the signal it starts with first, so call it signal 1, we emit signal 2, the confirmation pattern. And we just start with that, because as soon as it picks up a carrier when it's emitting, it switches to pattern 2 anyway. So let's scrap pattern 1 and just start with pattern 2 and see what we get. So I measured pattern 2, much quicker. You can see there it's high for 696 microseconds and quiet for 518. Those numbers don't matter. Again, they were just an input into what my device was doing. So this worked, like first time, which was cool. You can see the receiver picks up my emission, and the red line goes up, and the door's open. Cool, we're in. But there was something that was niggling at me, and that was that the first blue line over there is when I switched on the device. Cool, it works. But then after that, it goes quiet. Like there's no more blue until much later. Those red lines are where I didn't move the emitter. I just put my hand in front of it and took it away. And then it would work for a brief moment and then stop. And I had to do this a couple of times before it would trigger again. So this was a bit weird. Then we look at the data sheet and we go, oh yeah, there's features to suppress interference from fluorescent lamps. So this is probably what we're dealing with. I'm just blasting this pattern, and it's probably picking up as interference. Remember, this trace on the receiver is not from a microcontroller or anything. It's just from that receiver. So that little thing with those 6 or 7 blocks inside, this is what's emitting the signal. So everything about it is in the data sheet, and the suspicion was that we're picking up interference, which is a good thing, because if we can get around the interference rejection, it means that in a room like this, when there's 1,000 lights and everything's super bright and there's a lot of interference, we can get past that because it's going to reject the interference and it's going to listen to our signal if we manage to trick it into thinking it's valid. So in this case, I measured how long it pulsed for and how long it was off, came to this number, arbitrary 84. Again, doesn't matter, but this is what I did a hold off of 85 milliseconds between my transmissions so that it wouldn't get picked up as interference. So now it successfully works. I don't know where that slide went. It's gone now. And the only 2 components to it were to have the correct carrier frequency, which I measured, so I just implemented that straight up, and the correct pulse pattern for that particular device, to fool it into thinking that it's receiving its own reflection. So I'm going to try this. I'm going to see how it works. It was working in my office. I want to try a little bit further. So we're going to see how that works out. But my disclaimer is that I have sacrificed nothing and no one to the demo gods for this. So if it doesn't work, that's probably why. I don't have suspenseful music, but if you can just imagine that while I go and fetch the stuff, I'll be back in a second. Cool, this looks a lot like crime tools, I'm aware. Okay, so I'll just switch this on. This is a standard no-touch sensor. You've all seen them before. Kind of hard to see that it's working, so I've put a little light on the bottom here. Where is it? Yeah, there. So you can see that it's triggered a bit more easily. Green to blue from the back row is obviously hard. And you can see if you hold your hand there, it stays on. And at about 10 centimeters, it sort of stops working. So pop it over here. Let's go nice and far away. And see, I dimmed the lights as well for dramatic effect. Right, so I have a little targeting laser, which I thought would be cool. except even with the lights dimmed, you can barely see it. So it's just kind of annoying, actually. But this is my crime tool. And if we aim it perfectly, I hope this works. But wait, there's more. So this one's a little trickier, but it's kind of more representative of a real-world attack, is to have it bouncing off a surface. Just see if that LED is visible. Yeah, that's me. That wasn't my crime tools. So remember, I'm focusing this light through a narrow beam lens, so the aim makes quite a lot of difference. Okay, let me switch the lights back to normal. So, what is our conclusion? These things kind of suck. Right, so that's one device that I bought and experimented with. It works on that device. What about other vendors? What about different devices with slightly different timing? Like, maybe they're completely different, who knows? I know. That was another one that I got hold of from someone who, a guy who deals with this kind of stuff. And we tested that one, and what was interesting is the carrier frequency was different. It used a 31 kilohertz carrier, which doesn't matter beyond it's different to 30, but it didn't do a second sort of confirmation pattern. It just responded to the first signal I sent to it, which was fascinating because it actually looked like it was better built than that one over there. That was just the exact model that I had been eyeing and wanted to see if I could attack them. So that was interesting. It was easy to just hold it open because it wasn't really rejecting signals or confirming that there was a positive reflection. So yeah, sometimes appearances can be deceiving. Even if the thing looks like it's better, maybe it sucks as well. We did this. How do I do this? This was me in my garden. The green light means it's opening. I had this thing, I don't know, about 15 meters away, 10, 15 meters away, just switching between the two different carrier frequencies and the two different patterns, and just repeatedly triggering both of the devices. It makes a very cathartic clicking noise when it happens as well. So that was pretty cool. I have also tested on other instances of that exact device, and it does work, and of the other one I had. So the type, like manufacturing variations, don't seem to make a difference. We also broke into a library. I won't say where, but yeah, basically there was a bookshelf near the front door. So there was a pin pad where you could type in a code, or you could put your key card. I mean, they're a good couple of $1,000 for those things. But on the inside was a 270 Rand no-touch sensor. And just beyond that was a book. And I was easily able to just bounce it off the book. And probably through that glass door, about 10 meters down, was another door leading outside. And because of it being on the other side, I had direct line of sight. And I was easily able to trigger that as well. So, yeah. It works, and there's practical value to this attack. So the next steps, hopefully within the next week. I didn't take that out, and it didn't happen. That was for my dry run. So the X laser, I have implemented the X laser. Not so great unless you're doing crime at night, which I guess is not a bad thing. Being able to adjust the parameters. So if you encounter a device that you haven't seen before, being able to like just sweep through frequencies and see like on a little screen button with buttons to control it, like what you're doing would be useful. Portable unit, I'm working on this, and I'm hoping to have it by the end of the month, but we will see how that goes. And then being able to detect the carrier. So if you take a phototransistor and hold it up against a no-touch sensor, you can read what the carrier is. You can detect the emission from the LED. So not one of these fancy ones that decodes, but this this one in particular that actually it gives you the signal verbatim. And once you know the carrier frequencies, that's hurdle 1, then you just have to figure out the timing. And then I have to do some range tests. 30 meters I can, that's the furthest I've tested. Bouncing, haven't tested range, but I mean, in a well-lit room, this is more than enough for a practical attack, because in real life, you're probably going to be standing right by the door. So the distance is kind of a function of how far the wall is away from the sensor. And then how does glass impact it? I've done some testing on this. Normal glass doesn't seem to matter. I mean, I was going to bring a pane of glass, but it would look like this. You can see through it. Light passes through glass, we know this, and doesn't do too much for infrared. There's a bit of scattering, but for the most part, it passes through. Frosted and UV blocking glass, so this is quite an interesting one. If you are outside an office, the sensor's facing away from you and you have to bounce off something. If you manage to get access to the outside of the office, you could theoretically get line of sight through the outside windows into the office and see the physical sensor. The problem is often there's UV blocking, it's a film basically, that stops you getting from cooked alive in your office. It also blocks infrared, which is the heat part of it. So UV stops you from getting like actual sunburn, and the infrared blocking stops me from opening your doors, but also from you getting too hot. So I found that was very effective in blocking these attacks, and it was very frustrating because I wanted it to work better. I bought this. I'm amused that it is visible up to 2 nautical miles away, because it's sold in South Africa. I don't know what a nautical mile is. But it has been seen on TV, and it's military grade, and it's basically everything you could want. It's a cheap Chinese, sold by Verimark to make it sound fancy, but it's a cheap Chinese torch. So my plan is I've already taken it apart to the point where it no longer works, and I will try and implement something like this inside it. And obviously that looks a lot less sus than walking around with the tripod and, LED with a heat sink and a laser. Yeah. Then there were some iterations. So this was the sort of prototype number 2, was to just add the laser holder on the side, which is similar to what you're looking at now. Even if the laser doesn't work, one, it's useful to be able to see what the infrared LED is doing, but also I like that it says danger, and there's a red wire coming out of it, and it just feels more crimey and, And then the next version, which is what's in front here, it's the same thing, but with a holder for the PC board. So obviously you can't see that too well, but this is what it looks like. Yeah, now we're criming. I coined that. Please don't steal it. Yeah, and that's the X laser in sort of ideal. It was daytime, but not super bright. And this is a picture I took in my yard. Call it the Yeti because it looks like those Yeti sighting photos, but that was a super zoomed with my phone that doesn't have a zoom lens picture of the no-touch sensor on my neighbor's driveway across the road. I was standing by my front door shooting it through a palisade fence. So if you have line of sight, the range is crazy good. So that's pretty cool. Right, now that we've done crime, what are the answers? How can we address this? Because it's obviously not great that I can open this. I've already gotten into one place that I'm not supposed to be. I still need to tell them that I've done that. But yeah, it's a work in progress. So they're convenience buttons. They should not be used as security measures. That's the most important thing, which also means they shouldn't be used inside sensitive areas or where attacker would have line of sight. Even if you don't have a glass door, theoretically, you could get it under a gap under the door if you don't focus it as tightly. So that's what these additional notches are here for, is you can change the focus. You can make it a broader beam that doesn't, it's not as tight, but then your aim doesn't matter as much at the expense of range. So if you had a gap under the door and you managed to get enough light under there and you had ideal scenario on the other side of the door, you could open it through a solid door. If you didn't have a gap under the door, you could drill a small hole in the door. That's also easy peasy. If it's a white door, drilling a hole in the door is not hard. It's going to take a couple seconds, and you can cover it up with polyfiller and probably never, no one will ever see it. So the point is, there isn't really a practical way to prevent against this. only that they shouldn't be used for protecting sensitive areas. And the fact that they're inside the sensitive area is a misnomer because you can clearly trigger them from somewhere else. One of my colleagues, we used to have one of these in our office, so just in case you were wondering, we don't anymore. We have access control in and out. Unfortunately, it's not as a result of my research, but rather my colleague who managed to use a piece of wire and a paper and slide it through the door and hang it in front of the sensor. And that works too. So like you don't have to get fancy with lasers and stuff. You can just use a piece of paper and a wire. For the manufacturers, be stricter with tolerances. You can make this into a closed loop thing where it's much more difficult to spoof. So you can change the pattern. Because it's closed loop, you can have any pattern you want. As long as you're receiving what you're transmitting, you know that there's a positive reflection and someone's hand is 10 centimeters away. Hard mode is doing demodulation on the actual chip. You would have seen some of the tolerances are introduced by external components, such as the receiver. If you do that work yourself, that goes away, but it's a lot more development time, more processing power, all of that stuff. Probably not going to happen, more expensive. And then responsible disclosure. Who do I report this to? If somebody knows, let me know, because I don't. It's a really tricky one with hardware because it's implemented all over the place and poorly. Like, there's no brand name on that thing. I don't have anyone to go like, hey, you can't do this. If I go to the vendor that sells these things or resells them, they will probably not care because why would they? So it's a bit of a tricky thing to solve because, I mean, they didn't make the device is the point. So the only solution I can see is to sort of educate people and make it clear that this is not a great solution for what it's used for. So takeaways, be curious. All of this started because I saw the thing and went, hey, how could I like open that from, like how far away could I touch it from? So that's where the talk title comes from. It's lots of O's because it's far away. So ask the questions, not only of the hardware, like if you see something, but people. And something I've learned during this research, which has been really valuable, is asking people who don't have a hardware background, like just explaining this stuff. I had a great conversation with you the other day, Dom, about this stuff because, I had some questions and some like trying to figure out approaches, and you don't have to have a hardware background to come up with fresh ideas and different insights. If you don't understand how it's implemented, it doesn't stop someone from sharing their ideas or just new thoughts with you. So that's really helpful. And then ask people who do have a hardware background, like just collaborate, and like this stuff gets so much more fun when other people are involved. So that's my big thing. Other thing is break things, it's fine. Like when you break software, you just revert. When you break hardware, it costs money. That seems to scare people away. But 270 Rand in the greater scheme of things is like, it's not the end of the world. I didn't break any of them. That's the first one I bought. And some like attacks, when you have basic knowledge, there are things that you can figure out, what's dangerous and what's not. So, and the more you learn, the less likely you are to break stuff. So, like, don't be scared of breaking stuff. And then push through when it gets challenging. That is where all of like the crucial learning happens. So when I got to the point where I was like, cool, let's emit the pattern it emits and see what happens, and it didn't work, I was like, oh, okay, I'm tired of this now, I don't want to do it anymore. I hadn't learned anything. I'd done stuff that I already understood and knew, and it was easy. After that, it got tricky because, it didn't get that tricky. In reality, this attack wasn't that complicated. But in my head, I made it out to be. So, yeah, the hurdles were artificial. So keep that in mind. Sometimes when it's challenging, it's not actually challenging. You're just lying to yourself. And that's pretty much it. Thank you very much. Would anyone like to ask questions?
Any questions?
I'll just ask you, did you try a TV remote?
I did not try a TV remote. One thing I know about TV remotes is that they're almost entirely 38 kilohertz carriers, so that receiver wouldn't have even triggered. I could theoretically change the receiver to a 38 kilohertz receiver and see what happens, But no, I didn't try it because they're not compatible. No, this I made yesterday, and it's a variable, like proto board type thing, like generic, just holes to solder stuff into. I didn't want to be seen with a breadboard or an Arduino, so all of this code is proudly C. Yeah, so it's just a generic proto board. And in fact, there's no real need for it unless I want to produce more than like 2. But I think even the miniaturized version, I'm just going to dead bug components together and heat shrink the nonsense out of it. Yes. What kind of reflectors? Oh, no, I haven't. So the premise was that the mirrors don't scatter light at all, and retroreflectors would, if I'm thinking of the right thing. Oh, then no. I don't think I know what you're talking about. You can come and show me. Oh, like those? Okay, that's a good point. No, I didn't try that, but I might have a look. Remember, the limitation here is that the emitted light is so weak that like you can only get so far, and it's only line of sight. So I got 2 meters, whereas with this I could get 30. So this is the way to go. Cool. I think that's it. In the interest of time, I have run over. I'm sorry. But yeah, feel free to come chat about the stuff afterwards or anything. I'm happy to talk. Thank you very much.